Good morning. This is a presentation fulfilling the requirements of the CS551 Deep Learning project for the research survey. The group members are Jefferson Ori, that will be me, and Pallavi Pal and Priya Dastarwar. The topic of our presentation is machine learning or deep learning based approaches to object tracking. So in this presentation, we are going to go over three papers, then describe the state of the art of this specific application. And I'm going to present the paper Simple Online and Real-Time Tracking by Nikolai Voske, Alex Bewley, and Beatrice Polas. The method proposed in the paper uses deep learning and statistical techniques. The emotive problem can be viewed as a data association problem, where the aim is to associate detections across frames in a video signal. So simple in online and real-time tracking (SORT) is an approach to solving the problem of multiple object tracking with the objective to associate objects efficiently for online and real-time applications. The method involves detection, propagating object states into future frames, associating current detections with existing objects, and managing the lifespan of tracked objects. Objects are represented as bounded boxes. There's rectangles of varying sizes. Detection utilizes the faster region CNN framework, which consists of two stages. The first stage extracts the features and proposes regions for the second stage, which then classifies the object in the proposed region. The state of each target is modeled as a vector of 7 values. U and V represent the horizontal and vertical pixel location of the center of the target, while S and R represent the scale, area, and the aspect ratio of the target's bounding box respectively. The remaining three values are U dot, V dot, and S dot, which are the rate of change or velocities of the respective quantities. When detection is associated to a target, the change or detected bounding boxes used to update the target state when the velocity components are solved optimally using Kalman filters. If no detection is associated to the target, its state is simply predicted without correction using the linear velocity model. In assigning detections to existing targets, each target's bounding box is estimated by predicting its new location in the current frame. The assignment cost matrix is then calculated as the intersection over union distance between each detection and all predicting bounding boxes from the existing targets. The assignment is solved optimally using the Hungarian algorithm. Additionally, a minimum IOU is imposed to reject assignments where the detection into a target overlap is less than IOU minimum. When objects enter and leave the image, unique identities need to be created or destroyed accordingly. For creating trackers, we consider any detection with an overlap less than IOU mean to signify the existence of an untracked object. The tracker is initialized using the shape of the bounding box with the velocity set to 0. Since the velocity is unobserved at this point, the covariance of the velocity component is initialized with large values in order to represent this uncertainty. Additionally, the new tracker then undergoes a probation period where the target needs to be associated with detections to accumulate enough evidence in order to prevent tracking of false positives. Targets are terminated if they are not detected for T lost frames. Thus far, we have described basic SORT. In the paper, appearance information is integrated to improve the performance of SORT. Due to this extension, it is possible to track objects through longer periods of occlusion, effectively reducing the number of identity switches. The modification made to the previous approach are as follows. Scale area S is changed to hide edge, and an additional value, the rate of change of velocity of the aspect ratio gamma is included in the target state vector. Data association is changed in that now motion and appearance information is integrated through combining two metrics. The squared Mahalanobis distance between predicted Kalman states and new error measurements. And the smallest cosine distance between the ice track and the jet detection. Both these metrics complement each other. On the one hand, the Mahalanobis distance provides information about possible object location based on motion that are particularly useful for short-term predictions. On the other hand, the cosine distance considers appearance information that are particularly useful to recover identities after long-term occlusions when motion is not discriminative. There is a potential problem that can occur when there is large uncertainty, usually due to an object being occluded for a long period of time, which can cause increased track fragmentations and unstable tracks. To address this, a matching cascade is introduced. This is an algorithm which solves a series of subproblems instead of a global assignment problem for measurement to track association. Successful application of the method requires a good set of extracted features to be trained offline before the actual online tracking application. To do this, a CNN is used that has been trained on a large-scale person re-identification dataset, making it well suited for deep metric learning in a people tracking context. The architecture of the CNN is given here. The results of evaluating this new method were that identity switches were reduced by 45% compared to normal SORT. Track fragmentation increased slightly due to maintaining object identities due to occlusions and misses. A significant increase in the number of mostly tracked objects and a decrease of mostly lost objects. So, in conclusion, this approach returns the fewest number of identity switches of all online methods, including EMTT, POI, and SRT. It is possible to track for longer periods of occlusion due to using the tree-brain model. Thank you.
Hello everyone. The topic of presentation is multi-object tracking based on detection with deep learning and hierarchical clustering, which was published in 2019 IEEE 4th International Conference on Image, Vision and Computing, which was written by 4 students of College of Science, Hujiang Agricultural University, Wuhan, China. Introduction. This paper was introduced due to increased availability of video data. Therefore, we need a multi-object tracker. This multi-object tracking problem can be viewed as a data association problem where aim is to associate detection across frame in a video sequence. Here, they are developing a real-time tracking method by using hierarchical clustering after detection with deep learning framework. Now, if I talk about methodology, they are tracking with the help of detection and clustering, in which first step is data acquiring and pre-processing, in which they are tracking pig motion in the pig history, in which 6 pig histories were chosen for image acquisition and 10 videos were taken from each pig history. 3 segments were selected from 10 videos for test set and remaining videos are treated as training sample. Means 18 test videos and 42 training videos are there. Second step is object detection by mask RCNN. Mask RCNN extends faster than RCNN by adding branch for predicting segmentation mask on each region of interest. Mask RCNN has 2-stage procedure. First is region proposal and second is predict the class and box offset and also output a binary mask for each region of interest. Target is the area of each pig and a binary mask is predicted for each pig. Third step is clustering the detected object firstly, in which first we will split the video into frames images, then mask RCNN detects object and image and then it will acquire bounding box information. Then add new labels into bounding box information and in the second part arrange the bounding boxes in chronological order. Then traverse 24 images backward in turn for each bounding boxes. 24 is the value of m that we are choosing. Then find the maximum IOU, that is intersection of union from these 24 images. And if it is greater than 0.55, then we will merge the 2 boxes, otherwise skip that box. Then bounding boxes are divided into different classes and if the number of boxes in each class is greater than 7, then only proceed further, otherwise cancel this class. Now we will perform linear imputation of the discontinuous part of the time label in the remaining classes. Then again arrange the bounding boxes in chronological order in each class. Use shortest distance clustering method to cluster them in less than m classes. And And once you get number of classes is less than n, then again we will perform linear imputation for the discontinuous part of the time label. Now calculate the information of the last bounding box in the first class and the information of the first bounding box in the second class according to the equation. In the equation, delta D12 is the distance of these two bounding boxes, and delta D12 box is the ingredient of position. Delta D12 T is the ingredient of time, and beta is its weight. Result of object detection. It shows that the intersecting objects are detected correctly. Result of object tracking. Here, each individual is demonstrated by using a rectangle with the same color. It is shown that this method can detect and track people stably under different posture and blur level. Two pigs are tracked correctly and also two cats are tracked correctly under the condition of moving or changing shape or size. Comparing with other tracking method. This table shows the result of our tracker by comparing with other trackers in our labeled dataset. The first method is from the native API of OpenCV, and the second method is a tracker by using YOLO, V3 as detector and DeepShot as a tracker. Our method is a very good generic tracker and generalizes very well to our dataset, and the accuracy of this model reached at about 82.35%. Conclusion. This method can track multi-target effectively even if the size and shape are changing, and the multi-objects can be tracked effectively and steadily by using proposed hierarchical clustering. With this, I end my presentation. Thank you.
Timing multi-object tracking. The authors are Jungda Wang, Yizhuan Liu, Yali Li, and Segjing Wang. And those are from Department of Electronic Engineering, Tsinghua University. And the fifth one is Erling Zheng, and he's from Australian National University. So getting into this, let's get the intuition or the motivation behind this. So the conventional detection and embedding model, that is the separate detection and embedding model, comprises of two steps, that is the detection step and the association step. The detection step basically involves the localization of the targets, while the association step links connects the targets into the existing trajectory. And the two-stage model is another better variant of the SDE model. It is based on the region proposal network, same as the first region-based convolutional neural network, following a conversion to embedding model by replacing classification supervision with metric learning supervision. So both the SDE model and the two-stage model are not performance and speed efficient due to the inclusion of two phases, that is the detection and embedding or association. So both are using resampled pixels and the feature maps for the embedding purposes. So to beat the model on the performance and the speed wise, we have proposed a joint detection and embedding model, that is a one-stop single deep network framework to simultaneously output detection radius and the corresponding appearance embedding of the detected boxes. So based on the previous researches that has been done on the emotive tracking. So there are three categories. One is that model the association problem, a certain form of optimization problem on graph, and the second one is ones that make efforts to model the association process by an end-to-end neural network. Both are based on the convex graph inversion algorithms, where it is using many clicks or multi-cuts to gain the desired output. Here the nodes are the targets and the linkages are the embedding or association between graphs by compromising the loss. And the third one is the novel tracking paradigm other than tracking by detection that uses the detection incorporated with the tracker to get the embedding at the time of the detection. So the formulation So starting with the problem setting, the input are a unified large-scale multi-label data input set that has been formed using six datasets. The training datasets is a containing a nodes of three parameters I, B, Y, where IV is an image frame and B is the bounding box annotation for K targets in the frame and Y is the partial annotated identity labels. So the bounding annotation are present for all the elements of the dataset, whereas the Y, the identity labels, are present for some portion of the training dataset. And the output is the predicted bounding boxes, that is B cap, and the appearance embedding with dimension the F cap. The architecture is based on the feature pyramid network that makes prediction from multiple scales. A backbone network to obtain feature maps at three scales, that is 1 by 32, 1 by 16, and 1 by 8 downsampling weight. Then feature map from smallest to largest is upsampled and fused with earlier upsampled feature map to get the final result. Prediction heads are added upon feature maps. Prediction head consists of several stacked convolutional layers and output map size 6A plus D cross S cross W dimensions. So 6A plus D can be dismantled as the 2A cross S cross W, that is box classification, 4A plus S cross W, that is the box regression coefficients, and the D is the dimension a dense embedding map. So learning the detection. So the first step of learning the detection is redesigning the anchors in terms of numbers, scales, and aspect ratios to be able to adapt to the targets. So here the aspect ratios has been set 1:3 for better result. Anchor templates are set to 12 such that A is equal to 4 for each scale and the scale widths of anchors range from 11 to 512. So secondly, select proper values for dual threshold used for foreground and background assignment. So intersection over union, if it is greater than 0.5 with respect to the ground truth, approximately ensures a foreground. If it is less than 0.4, so it would be regarded as background. So the loss function that has been categorized as two loss functions, the foreground and background classification, that is L alpha, and the bounding bifurcation is L beta. L alpha is basically a cross entropy loss, whereas the L beta is smooth L1 loss. So learning appearance embedding. So learning appearance embedding consists of the triplet loss, upper bound optimization of triplet loss, and cross entropy loss. The loss is here to gain the insight about which instances of the targets are close to each other and clustering those, whereas differing those who are far from each other. So F triplet is maximum of 0 to Ft Fi minus minus Ft F plus and summation of I to M, where Ft is the mini dash gradient of the anchor, where Fi minus is the negative sample with respect to Ft, where F plus is the positive sample with respect to Ft. So upper bound optimization and triplet loss is being considered to gain the triplet loss with more stability and converging speedily. So L upper is defined as log 1 plus summation of I exponential ft f minus and minus ft f plus, but where we can manipulate those and we can get that minus log exponential of ft f plus whole divided by exponential ft f plus plus summation of exponential ft f minus. So here it is mostly similar as the cost entropy loss. So we can divide the cost entropy loss, that LCE is minus log exponential of ftg plus whole divided by exponential ftg plus plus summation of exponential ftg minus. So as per our study, the LCE greater than L upper is greater than L triplet, and in the cross entropy loss, G plus is the average weightage where the anchor resides, and G minus is the negative weightage samples. So let's get to the automatic loss balancing. So automatic loss balancing is the phase where JDE actually comes into play. So joint objective can be written as a weighted linear sum of losses from every scale and every component. So L total is the summation of I to M, the summation of J alpha beta gamma WGI LGI, where LJ is the log function over alpha, beta, gamma, and Wj is the weight related or associated with the Lj, and I1 to M are prediction heads. So formally, the learning object with automatic loss balancing is written as L total summation of 1 to M, summation of J, alpha, beta, gamma, that is our losses, 1 by 2 Lji divided by is L to the power Sji plus Sji, where Sji is the task-dependent uncertainty for each individual loss. So online association, although the main focus of this JDE paradigm is nothing to do with the online association or any type of association, but to get our desired result, we are using this method. So Twatlet is described with an appearance state e to the power I and motion state mi, that is a top of x y gamma is x dot y dot gamma dot s dot. So s x y are the height and the center of the boundary boxes coordinates, and x dot is the velocity along with the x-axis. Throttlet appearances EI is initialized with the appearance embedding of the first observation Fi0 of the element I. We compute the pairwise motion affinity matrix AM and appearance affinity matrix AE. We do all the observation and the throttles from the pool. The appearance affinity matrix A is calculated by the cosine similarity matrix, where the motion affinity matrix AM is calculated by Mahalan-Morris formula. Then solve the linear regression problem by Hungarian algorithm with cost matrix C is equal to lambda AE plus 1 minus lambda AM. Motion state mi of all mass structures are then updated by Kalman filter. The appearance stated Ei is updated by EIT alpha EIT minus 1 plus 1 minus alpha FIT, where FIT is the teeth of the at the time t, the appearance embedding of the observation. So here is the table that we get for this online illustration with comparing our method with the previously defined SORT method with low density and high density dataset. The low density is the MOT15 dataset, where the high density is the CVPR 1901 matrix. So we can see clearly that with the MOTA, ITF, and FPS, that means frame per second, multi-object tracking accuracy, and inverse document frequency, and that the ours proposed method JDE is overpowering SORT. So here is the overall result. The FPST, FAS, and FPSA are basically the detection, that is the for D, and association for A, and overall speed of our different methods, and this is the accuracy that is being calculated for the overall calculation of embedding and the detection phases cumulatively. So we can see that the speed is better with the both the JD864 and JD1088 as compared to any of the previously mentioned method, that the DeepSearch, RR16, TAP, CNMTT, and PI. Although the accuracy of the PY is 60.6, 66.1, and the JDE is almost 64.4, but it's near to real. So let's get a sample query target in real time. The query is a pedestrian target, and the target is the feature maps that we have extracted, and we have calculated the detection similarity and the embedded similarity using the question similarity and this other paradigm of embedding. So using the TPR, the true positive rate and the false alarm rate, we have seen that the Visualization of the retrieval performance is quite similar as expected. So the JDE, that is joint detection and embedding, is performing very well and as expected in real time. So to conclude, we can conclude that our design significantly reduced the runtime of a multi-object tracking system, making it possible to run at a near real-time speed, and the tracking accuracy of our system is comparable with the state of the online emoting method. So that's all from my side.
Now we discuss the state of the art for MLDL based approaches to object tracking. There are three approaches to being used to build AI trackers. First is convolutional neural network based offline training trackers. This is one of the early series of trackers which apply the discriminative power of convolutional neural networks to the task of visual object tracking. Gottern is one such offline learning tracker based on convolutional neural network which doesn't learn online at all. First, the tracker is trained using hundreds of videos or thousands of videos for general object tracking. This tracker can be used to track most of the objects without any problem, even if those objects were not part of the training set. Number two is convolutional neural networks based online training trackers. These are online training trackers which use convolutional neural networks. One such example is multi-domain neural network (MDNet), which was the winner of the VOT 2015 challenge. Since convolutional neural networks are computationally very expensive to train, these methods have you to use a smaller network to train at fast speed during deployment. However, smaller networks don't have much discriminative power. One option is that we train the whole network during inference, we use the first few layers as feature extractor. That is, we only change the weights of last couple of layers which are trained online. So we have the CNN as feature extractor and the last few layers as can be quickly trained online. Essentially, our goal is to train a generic multi-domain CNN which can distinguish between target and background. However, this poses a problem during training. The target in one video could be the background in another, which would just confuse our convolutional neural network. So MDNet does something clever. It rearranges the network into two parts. The first part is the shared part, and then there is a part which is independent for each domain. Each domain would mean an independent training video. So the network would first train over k domains iteratively, where each domain classifies between its target and background. This helps us in extracting the video independent information in order to learn a better generic representation of trigger. After training, the domain specific layers are removed and we obtain a feature extractor, shared network above, which can distinguish between any target above object and background in a generic way. During inference production, the initial shared part is used as a feature extractor and domain specific layers are removed and we add binary classification layer on top of the feature extractor. This binary classification layer is trained online. In each step, the region around the previous target state is searched for the object by random sampling. MDNet is one of the most accurate deep learning based online training detection-free single object tracker. Next, number three, we have LSTM plus CNN based detection based video object trackers. Another class of object trackers which are getting very popular because they use long short-term memory LSTM networks along with convolutional neural networks for the task of visual object tracking. Recurrent YOLO ROLO is one such single object online detection based tracking algorithm. It uses YOLO network for object detection and an LSTM network for finding the trajectory of target object. There are two reasons why LSTM with CNN is a good combination. LSTM networks are particularly good at learning historical patterns so that they are particularly suitable for visual object tracking. LSTM networks are not very computationally expensive, so it is possible to build very fast neural network trackers. Input frames go through the YOLO network. From the YOLO network, two different outputs, image features and bounding box coordinates are taken. These two outputs are given to the LSTM network. Then LSTM outputs the trajectories bounding box of the object to be tracked. The preliminary location inference from YOLO helps the LSTM to pay attention to certain visual elements. ROLO explores the spatiotemporal history, that is, along with the location history, ROLO also explores the history of visual features. Even when YOLO detection is flawed due to motion blur, ROLO tracking stays stable. Also, such trackers are less likely to fail when the target object is occluded. Recently, there are many more LSTM-based object trackers which are much better than ROLO using many improvements. Now, here are the current deep learning-based MOT algorithms. These methods are organized according to the functionality of deep networks and the way of state optimization. In online MOT framework, main challenges lie in how to learn robust associating metric of linking the detections to tracks, when to create new tracks by distinguishing the true detecting results from false positive ones, and when to terminate the lost track. Specifically designed, the deep learning methods provide compromising solutions to these challenges. Deep sort and CDA/DDL return the appearance features from person reality verification tasks to associate with detections. RAN and MIR predict motion and appearance features by autoregression and matching classification using a long short-term memory LSTM networks. STAM MOT applies spatial and temporal attention map to handle the partial occlusion problem in tracking. Recurrent neural network LSTM, RNN and LSTM designs end-to-end deep neural network to learn the association between tracks and detections. Statement update, initialization, and termination of tracks like particle filter as in HWDPL. To find the optimal location of objects, STAM MOT deploys the dense searching strategies, which are utilized commonly in tracking single object. Two deep learning based methods using MHT framework are MHTDM and MHTBLSTM, in which the CNN and bilinear LSTM networks are employed to learn appearance features. In the offline MOT framework, the main challenges are how to construct the graph and network and how to optimize the global leveling problem of them. In order to handle the problems of offline tracking, detection to detection pairwise similarity as well as those between short tracks is learned in CME, CNN, and CNN TCM. To obtain more accurate similarity metric, the additional information such as temporal sequential order is considered in quad CNN. These sequential features are strengthened in GCRA. Further, researchers find that network optimization such as multi-cut flow can be improved by deep flow features in joint MMC and lifted cut edges in LMP. Besides, network flow can also be optimized globally in end-to-end learning manner in deep network. Through the exploration of deep learning algorithms and MOT frameworks, it is proved that deep learning is effective in improving tracking performance from aspects of tracking predictions and data association. Similar as in image recognition tasks, learning appearance features automatically by deep CNN can promote discrimination and robustness to occlusion for both for online tracking and offline optimization. Besides, learning motion features by recurrent neural network are also helpful to promote the accuracy of motion prediction, thus to improve the performance of bipartite matching between tracks and detections. By comparison with appearance and motion features, learning relatively less end-to-end detections learning algorithms are explored for the complex components between both in offline and online tracking frameworks. It is desired that more approaches can be inspired from the work of RNN, LSTM, and NetFlow, which obtain the tracking results directly by end-to-end learning process. As stated above, there are different functionalities of deep networks when they are employed for MOT. Basically, deep features which are learned from the related tasks, person identification, can be combined to promote the tracking performance. Additionally, the specific neural networks can be designed to promote discrimination between different objects or regressive accuracy for one object. Thus, features learned from these neural networks are robust to disturbances between tracking. Further, some end-to-end deep learning architectures for MOT are proposed. These architectures try to model the whole procedure of tracking, always with some assumptions for tracking component. For example, RNN LSTM assumes global existing probability of objects, and deep network assumes first-order dependency for linking. With this, we come to the end of our presentation. Thank you for your attention.